invitation. I will be talking about ERS, instability, and the D1-D5 CFT. This is based on this paper, and my collaborators on this are Bidisha and Deb. Okay, so before I move on with the talk, I will show one fun slide. So I have been visiting TFR for last 7 years. 7 years ago, I joined India as a faculty, and almost every year I have been visiting at least once, and thank you very much for the invitations and so on. Okay, so the scope of this talk is that are fuzzballs, smooth solutions, or microstate geometries, are these solutions classically stable? So this is the question that we are interested in this talk. And surprise of a surprise, I will argue in this talk that fuzzballs, as we know them today, they have been argued to be classically unstable. And this instability is known as the ERS instability. So in most of this talk, I will give an overview of this subject. And ERS stands for these three authors, Eperon, Reall, and Santos, and the paper came out in 2016. Okay. Yeah, in the second part, I will discuss what we know about it from the D1-D5 CFT and our paper. Okay, so here is the outline of my talk. I will start with some introduction and things that I have said before in this room about black holes. I will review some of those things. Then I will talk about ERS, then our recent paper and summary.
Are you going to agree with ERS or?
Yeah, well, you will see. I mean, yeah, it's a detailed discussion. Yeah. Okay, so let me start with the introduction. So stability of non-extreme black holes is a topic that is favorite among relativists, and this has been studied for more than 50 years now. So mode stability of linearized gravitational perturbations of short-shelled and curved black hole is studied in a huge detail, starting with the work of Rijay, Wheeler, Vishweshwara, and so on. And one famously find that there are no unstable modes when we study this system. However, this is not enough to establish the full linear instability of the black hole. There are many open issues. The question of completeness of quasi-normal modes is not addressed. Typically, these quasi-normal mode wave functions diverge at infinity if the imaginary part of the frequency is negative. So the infinite superposition of these modes is in question, and there are several issues of this type. So linear stability is not fully established by only studying quasi-normal modes. And these issues I have discussed here and also in this talk at ICTS I gave in 2017. Okay, so just to review how this mode analysis works is that we start with the box phi equal to 0 on your favorite black hole background. Then what we do is that we do a mode decomposition. When we do this mode decomposition, the art is to find this function psi, appropriate combination of variables r and derivatives of r or whatever. So the art is really to find this function psi of r such that this function psi of r satisfies a Schrodinger equation. And this, once you obtain the Schrodinger equation, then there is standard technology for studying these perturbations. So I must say that no matter how complicated the system is, gravitational perturbation on curved black hole, higher spin perturbation on curved black hole, almost every system can be reduced to this Schrodinger type problem, and this is where the mode stability discussion starts. Okay, so going beyond mode stability, these two mathematicians, de Farmas and Rodinansky, in 2005, and after that there has been many generalization of all of this. They gave a proof for the stability of short-shelled solution, and I will just give the statement of the theorem that they prove. So what they say is that prescribe initial data phi and phi dot on some initial hypersurface sigma 0. So here is some surface sigma 0 which intersects the horizon. And the only condition that they require is that the scalar field goes to 0 at infinity, phi goes to 0 at infinity. With this, only this much assumption, they were able to show that a scalar field at later times decays with some positive alpha. So a scalar field, if you go to a future slice, then the value of the scalar field decreases. Okay, and the decrease is such that a scalar field goes towards 0 everywhere on and outside the horizon, and all the derivatives of the scalar fields also decay. Okay, so from physics perspective, this is very expected result. This is, if you wish, a dynamical version of the no-hair theorem, and it, I mean, these two mathematicians proved this thing rigorously. Okay, so the proof of this theorem is very long and complicated, but what plays very important.
Decays, say again, decays on the horizon.
Yeah, decays everywhere outside the horizon and also on the horizon. So everywhere on and outside the horizon.
I see. What about if I had just a scalar going a pulse of describe plus? Would that be counted as a decay?
Yeah, that will be called as a decay.
Because
Yeah, it just decays. Yeah, yeah. Okay.
So all the surfaces have the common property that they go to the space like.
Yeah. Actually, yeah. So this is the question that Shiraz is asking a little bit different. So here, what I am talking about is that the surfaces evolve in this direction. Yeah. Okay. So the proof is very long and complicated, but what plays very important role in this discussion is the so-called local horizon redshift effect. And this is nothing fancy. I mean, this is an effect we teach in our GR course, but may not have been appreciated in this language. So the effect is that there is a redshift factor along the horizon, which is e power minus kappa v. So the effect is just as follows. Suppose two observers A and B are such that A crosses the horizon, but B does not. So observer A crosses the horizon and B does not. A emits signals at constant frequency in his proper frame. Then the frequency at which the observer B receives these signals are shifted to the red. This is the standard GR effect that we teach in our courses. The only thing that is perhaps not emphasized so much is that the effect is local. So if observer A falls in and observer B falls in a little later, then also there will be a redshift, and the redshift will be e power minus kappa v. Okay, so so the situation changes very much for extreme black holes, and I want to discuss extreme black hole especially because I want to talk about fuzzballs. So for extreme black holes, there is no such redshift effect because kappa is 0, and since kappa is 0, in fact, one can write down a conservation law at the horizon, and it is remarkable that this conservation law was not discovered by physicists. I will explain what this conservation law is. It proceeds as follows. So write the Reisner-Nordstrom, extreme Reisner-Nordstrom metric in Eddington-Finkelstein, ingoing Eddington-Finkelstein coordinates. So V are theta phi coordinates, and then evaluate the wave equation box phi at r equal to m. So evaluate the box phi at r equal to m. And for simplicity, consider the mode L equal to 0. So when we just do this very simple calculation, we find that box phi at the horizon takes the following form: del by del V acting on some combination equal to 0. So since this combination acted on by del V is 0, this combination does not change along the horizon, and this is the conservation law that I am talking about. So earlier I said that for Schwarzschild black hole, the value of the scalar field or all the derivatives of the scalar field decay along the horizon. But here is an example where this is not happening. Just by studying extreme black hole where there is no redshift, we are able to see that this is a quantity that remains constant along the horizon.
What happened to the angular derivatives?
Actually, here I have set L equal to 0, but similar discussion can be generalized for L not equal to 0.
So just the fact that this f of r has a double 0.
Yeah, that plays a very important role. Yeah, so you get a term which is like derivative acting on f of r, but since f of r has double 0, when you evaluate it at r equal to m, that term vanishes. Yeah, indeed, that's how it comes about. Okay, so for a spherically symmetric scalar field, we see that this quantity is independent of V, so it is conserved along the horizon, and this is the simplest example of the so-called Eretikis constant. So since this combination is conserved, you see, since this combination is conserved, it cannot happen that both phi and del r phi decay at the horizon. If phi decays and del r phi also decays, then this quantity cannot remain conserved. So a combination of this has to remain the same. And what Eretikis showed in his paper is that scalar field decays. Okay, and since scalar field decays, this quantity cannot decay. What is important for the rest of this talk is the fact that the scalar field decays. Actually, the discussion of derivatives not decaying, I have given a talk here last year on this subject, so I will not go into the derivatives not decaying. Okay, and there is a
It doesn't decay, in fact, it has to grow. That's what
not necessarily grow as a function. Yeah, I mean the second derivative of scalar field has to grow. This quantity has to remain constant. The equation was that in V, yeah. So this quantity has to remain constant, but indeed one can argue that the second derivative of the scalar field will grow. Yeah. Okay. With V, yeah. And that thing is known as the Eretikis instability. Okay, so there is a physical way of understanding this. Physical way of understanding is the following. So take the stress tensor of the scalar field as seen by the infalling observer. Infalling observer will have partial r as the vector parallel to the trajectory, and then the stress tensor will be TRR, which is del r phi squared. So earlier I argued that there is no redshift effect. So photons traveling on the horizon do not get redshifted, so the energy remains the same. And this is just saying that there is energy present at the horizon at all times, because del r phi is not decaying, and it's just the reflection of the fact that there is no local horizon redshift effect, no local redshift effect along the horizon. Is this point clear? Photons straddling the surface of the horizon, they remain there at all times. Okay. Okay. So main lessons from this discussion. Actually, this was a bit of a review. I have given a longer talk on this earlier. So the main lessons of this discussion is that extreme black holes have peculiar properties at the horizon. But whatever be the properties, what is important for us is that scalar field decays with an inverse power of time everywhere outside the horizon, in fact also on the horizon. And although I did not discuss this in detail, but from the work of Eretikis, one can indeed, it follows that higher angular momentum modes decay faster, and the Lth mode of the scalar field decays like t power minus 2L minus 2. So
and the normal derivatives for these higher angular momentum modes, they also decay?
The first derivative, some del L r, this quantity will not decay, but del L plus 1 r will grow up. Yeah. Okay, so this was the introduction. The only message is that the scalar field is decaying on the horizon and outside the horizon. And now I will discuss the ERS instability. Okay, so a question that has bothered a lot of us is why the properties of scalar field on black holes are so different from scalar fields on fuzzballs. Suvrat and his student Pushkal has written a paper on this, and these authors have also written a paper on this, and there are various other discussions. This paper caught our imagination, so I will discuss this. I must say that different people have different viewpoints. My viewpoint on this subject is that classical properties of black holes should emerge from the fuzzball proposal. Others do not share the same viewpoint. In particular, I am of the opinion that decay properties of the scalar field of a black hole should have an understanding from the fuzzball proposal. And it's unfortunate that this does not seem to be the case. So Eperon, Reall and Santos have argued that this does not seem to be the case, and there is a debate on this topic, so I will present the arguments and the debates and all those things. Okay, so I will present the ERS arguments. To my taste and knowledge, they are very robust and I don't see a way around them, and then I will present the main points of the debate. Okay, so in order to set the stage, I have to say a few things about the fuzzballs that I am talking about. So the calculations most concretely so far has been done for the Bena-Warner geometries, but the setup is so general that it applies to almost all solutions that have been constructed so far. So I will just give a one slide introduction to what these things are. So in 5-dimensional supergravity, a very large class of supersymmetric solutions exist, and these solutions are asymptotically flat. They are stationary, that is to say that they have partial t as a Killing vector, and this Killing vector is time-like at infinity. And supersymmetry guarantees that there will be a causal Killing vector, and partial t is taken to be that Killing vector. Okay, these geometries are geodesically complete, have topology r times sigma. So r times sigma means they are globally hyperbolic, and sigma has topology. So I mean they have non-trivial 2 cycles. That's why they are called bubbling solutions. Okay, these solutions typically are rotating. Non-rotating solutions are not known, and they have horizons. No horizons. Sorry, they have no horizons. Okay. So for simplicity, I will focus on the 5D perspective because in 5D it's slightly easier to picture these geometries. But for calculations and for studies, it's better to work in 6 dimensions. Okay. So one of the funny properties that these geometries have, and this was already noticed by Bena and Warner when they wrote the solution, but emphasized very much by these authors, Gibbons and Warner. So the Killing vector partiality is time-like everywhere except at a time-like surface where it becomes null. So this is the surface where these sort of bubbles sort of meet, and on this surface this vector becomes null. So for some people or for initial discussions, it was thought of as a plus point because this is a surface where the vector is becoming null, so there is some infinite redshift, some feature of horizon perhaps, but we will see that this is very bad. So this is a surface which is a ergo surface, but it has no ergo region associated to it because partiality is time-like everywhere outside except at this surface it becomes null. Okay. So what this means is that if we look at the norm of this vector v, which is partiality, this quantity is minimized at this surface because this quantity is positive everywhere, and at this surface it becomes 0. So if we take derivatives parallel to the surface, then it remains 0, but if we take derivatives perpendicular to the surface, then also it remains 0 because the norm of this vector is minimized.
This is the 2 charge.
Actually, it's true for all fuzzballs that are known, but in particular for 2 charge and 3 charge. Yeah.
So this aspect is true also for the 3 charge.
Yeah, this aspect is true for the 3 charge. Actually, as I said, I have tried to simplify this discussion by sticking to 5 dimensions, but appropriately, like playing with 5 and 6 and finding the right Killing vector and so on, the statements are all true for 2 charge, 3 charge, and in fact for all fuzzballs that are known.
So what dimension was sigma?
Sigma is a surface which is 4-dimensional surface. So I am writing it as 5-dimensional solutions, and I am separating out the time. So sigma is a 4-dimensional surface. Okay, so now this surface is very dangerous, and this is the key point of Eperon, Reall, and Santos. So this surface, the evanescent ergo surface, is ruled by 0 energy null geodesics. So okay, please have patience. This is like one slide of GR kind of discussion. So consider this vector v and consider the geodesics tangent by generated by this vector. So okay, so since this vector is killing, so I can change this, and since I can change this, VB comes here, and I argued that this quantity is 0 on this surface. So we see that particles which are following partial t as tangent vectors, these are geodesics. Okay. Now, so first statement is this, that V is tangent to the geodesic. And now the next statement is that this is tangent to a null geodesic because V dot V is 0 on this surface. The next thing is that it is tangent to a 0 energy null geodesic because the energy is minus P dot V, but P is proportional to V, so V dot V is 0 again. So we have a situation which is very bizarre. So situation is that we have a time-like surface ruled by null geodesics. Okay, this typically never happens. The case which we teach in our GR course where it happens is the photon sphere of Schwarzschild, where again null geodesics are like bound on this surface, but they don't have 0 energy. I mean, they have finite energy and they remain on this r equal to 3m surface. But that is the situation that comes closest to this discussion. But the situations for fuzzballs, in particular for this surface, is very peculiar. Okay, so for photon sphere of the Schwarzschild, the situation is quite good because the trapping of geodesics is stable, is unstable. So the idea is that a null geodesics on the photon sphere at r equal to 3m of the Schwarzschild solution is trapped. Trapped in the sense that it remains at r equal to 3m surface at all times. However, the trapping is unstable because if we disturb this geodesics, either they fall into the black hole or they escape to infinity. Okay, and similar phenomena has been well studied for the Kerr black hole. In fact, using geometrical optics or WKB methods, one can determine real and imaginary parts of quasi-normal modes of Schwarzschild or Kerr solutions and relate them to these geodesics. This has been done in a series of papers by various authors, but this paper particularly discussed in a lot of detail this geometrical optics in the Kerr black hole thing. Okay. So for evanescent ergosphere, the situation is very bizarre, and we have a stable trapping of geodesics. It's stable because the geodesics have zero energy. So these are zero energy null geodesics on this surface S. These geodesics are minimum energy, so they cannot go further down. There is actually nothing further down, but they also cannot come out because it costs energy for them to come out. So these geodesics are completely stuck there. They don't have any place to go. Okay, because there is nothing anyway below, so they cannot go down, and they cannot come out because coming out costs energy.
By energy, you mean like energy in this effective potential for the geodesics?
What I really mean is the killing energy, P dot V,
Okay.
but one can also view it in that way. Yeah. Okay, so this is very peculiar. It doesn't happen typically. So now, if we use geometrical optics methods, one can try to determine the real and imaginary part of the quasi-normal modes associated to these geodesics, and we expect that the real part of the quasi-normal modes will be close to zero because they are zero energy geodesics, and we expect the imaginary part of quasi-normal modes to be very small because these geodesics are completely stuck.
Just so in case of the photon sphere,
Yeah.
you say that these photons are unstable because they can either go in
Yeah.
or go out.
Yeah, if you so they are trapped in the sense that if you don't disturb them, they will always remain at r equal to 3m surface.
So there are some positive energy, so they would like to minimize the energy, let's say spontaneously, so they would go in or they would go in by itself.
It's the top of a barrier. You can think of it.
Either way.
Yeah, yeah. Either way, yeah. Okay, but in this situation, the situation is reversed, so they are stably trapped now.
I didn't understand how you could. Sorry, you said something about determining the quasi-normal modes from these spheres. I didn't catch that. Could you say that again?
Yeah. So so consider a situation when the L value of the quasi-normal mode is high. So large L modes. So here one can use the geometrical optics approximation. In the geometrical optics approximation, the value of the scalar field will be localized on some geodesic, and those are the, so one can make a relation between these geodesics and those quasi-normal modes. And by studying how fast these geodesics want to deviate from each other, one can determine the imaginary part of the quasi-normal modes, and by studying the energy of these geodesics, one can study the real part of the quasi-normal modes.
And so somehow the point is that once the mode goes inside the photon sphere, it just keeps going through the horizon. It won't bounce back again.
That is determined by the effective potential. The effective potential, okay, another way of saying this is that if we look at the effective potential of the scalar field and take the large L limit,
yes,
the potential become exactly the same as seen by the geodesics.
Yes.
Yeah.
Yes. But what's puzzling me is that you're doing some local analysis around the local maximum.
Yeah.
And then making some statement of the full quasi-normal.
In the geometrical optics approximation, that is the only part that becomes important. So the in the large L limit, the part of the potential that becomes important is this. Yeah. And if we draw the potential for the time-like geodesics, it is slightly different, but it is also of the same type.
Fine.
So since the two potentials are the same, and we are looking at large L limit,
where is the horizon in this line?
the horizon is here. Yeah.
Is here.
Yeah.
And it's sloping downwards.
Yeah. I mean, here the decay is exponential in the situations of non-extremal black hole. The the decay is exponential, and here the decay is power law.
And so the fact that that is unstable allows you to. Yeah, so
Yeah.
I'm sorry
Yeah.
to be so slow, but you did some local analysis.
Yeah. So I did some local analysis here, and I found the curvature of this potential and so on. And that will tell me how these geodesics want to deviate. Like if I start with two nearby geodesics, how they want to deviate, and that will determine the rate of instability.
You're saying the longest lived geodesics stay very near the top, and therefore how long they stay near the top determines the lifetime of these.
Of the, yeah, you can put it like this.
Right.
Yeah. Okay, so so you see here the situation is very peculiar. If we do the same analysis, then we expect that the real part will be close to 0 because these are 0 energy geodesics, and imaginary part to be very small.
So non-zero energy null geodesics are they also trapped on the surface? What is the potential?
No, actually non-zero energy are not of that type, because if we calculate, if the reason, so the energy is 0 because P dot V also became 0. So if P dot V is not 0, then these are not on this surface.
Null geodesics, there's only one set of null geodesics, and they have zero.
Yeah. Okay, so
This need not be on that surface, so go away.
yeah. So away there can be geodesics, but
They'll be bound in some region.
no. So those ones are not trapped. I mean, they are. I mean, no.
Potential.
The potential, I think, is something like this. Yeah. So in this region, the geodesics are stably trapped, and this is what we are discussing.
But if you increase the energy slightly,
Yeah. So then again, I mean, I think there will be a sense in which they are bound in that region. Yeah. Yeah, I do believe that they will be bound, but I have not studied those ones. Yeah. Okay, so the main lesson from this discussion is that we expect the quasi-normal modes, the real part of the quasi-normal modes to be close to 0, and imaginary part to be very small. Okay, and this was the intuition, and this
part will be very small because there was because it's a minimum.
is the meaning. Yeah, the perturbation gets trapped.
Yeah.
Yeah, it doesn't want to decay. Yeah. So this was the main intuition, and this was the main calculation that these authors did. So they computed the quasi-normal modes of 2 and 3 charge geometries in the large L limit, and indeed they found that the real part of the frequencies goes as order L to the 0, and imaginary part of the frequencies goes as minus L log L. Okay. So these modes are very, very slow, much slower than anything that was known before, and this was really a surprise.
This is an asymptotically large L.
Yeah, in the large L limit, yeah. Okay, the reason I say this is anything not known before, because Festuccia and Liu famously calculated the quasi-normal modes of large ADS black holes, and what they found is that there are slow decaying quasi-normal modes, and these slow modes were omega r becoming of order L and omega I becoming of order minus L. And the reason for these modes was that if you are in ADS space with a black hole around you, so this is a black hole, then there are geodesics with large angular momentum which are like circling the black hole at large values of L, but since they have large L, they cannot come close because they have large L, they have high angular momentum. So the energy of these geodesics go as order L, but also they cannot go anywhere else because I mean, if they try to go to the boundary, they are bounced back. So they remain in the region close to the boundary of the ADS, because they cannot come in because they have so large angular momentum, and they cannot go out because they are bounced back from the boundary of ADS. So these geodesics are also stably trapped, and because of this trapping, so this trapping is in a non-compact region because the r equal to infinity at the boundary, and And from there one can argue that there are quasi-normal modes which are e power minus L, behave like e power minus L.
That L is like the area under the curve for tunneling.
Yeah, exactly. Yeah. So I mean, you can ask like why at all why at all there is a negative imaginary part, and that is because these are waves. So these waves will eventually decay. These are not exactly geodesics. So Festichi and Liu argued this, but you compare this with this, the quasi-normal modes of these fuzzballs are really very slow.
So you have the beta appearing over here.
Yeah.
You have the jet pressure appearing.
No, it's not beta. It's some number.
How is it now?
Yeah, it depends on the mass of the black hole and things like those. It's just some number.
And
Yeah.
I'm thinking of this exponential of minus beta L as the tunneling rate to go to the place where the potential is more negative.
Yeah. I mean, so the only way these modes can is because of the bouncing feature. The only way these modes can decay is by falling into the horizon. So slowly, very slowly, these things will decay and fall into the horizon, and
Yeah.
this is what is captured
But
by.
up there,
Yeah.
but there was no more negative place for them to go to.
No, so there is a place for them to go to. So there is this barrier. So through this barrier, they can tunnel to asymptotic, to asymptotic infinity.
And there the energy is lower.
Zero energy geodesics.
So
Yeah.
0 goes to 0.
Yeah.
Okay. So it's just a little bit above 0.
Yeah.
And that's
Yeah.
probably the reason for the extra energy.
For the
Okay.
So why is it
Huh?
also the height of this barrier?
Height of the barrier, but I was thinking that it also probably there's a width factor, because if they've got they've got a little bit of energy above 0, they'll have to go very far before they can come out there. So probably the height times the width is that extra long. I was thinking.
I mean, I haven't thought in those terms,
Okay,
but
okay. And that energy is a 0-point energy because it's a wave.
Yeah. That's roughly.
yeah. Okay. So this is the main. So the intuition for the omega r is actually the way these people argued, and the way these people like came up through this idea through the maze of equations, is that in the large L limit, in the geometrical optics limit, we expect geodesics to correspond to the energy of the geodesics to correspond to the omega r of the quasi-normal mode. And since by previous argument we saw that we expect zero energy geodesics, if we search in the parameter space, we expect there will be a set of.
Is the curvature around the minimum independent of L in the large element? Because I would have expected that your correction to be as Gautam said, to be the harmonic oscillator energy.
Yeah.
And you're saying that's order L to the 0, which suggests that this shape has a good large element. Is that the case?
Well, I don't think I can answer this question. I have not looked at the potential in this way, but looking at the formula, it looks like that the potential certainly depends strongly on L.
Yeah.
But whether the curvature at r equal to 0 depends on the L, that I have to think. Okay, but this is the main physics slide, that because of this zero energy geodesic discussion, these people argued and searched, and they indeed found that there are quasi-normal modes of this type. And
Remedial question. What is the
Geometrical
geometrical optics limit?
optics limit is large L limit.
Why?
Because of this reason, that if you study the scalar potential and potential for geodesics, then in the large L limit, the potential for scalar and the geodesics, they match. Yeah. So one can expect that if we find modes at large L, they will have some correspondence with geodesics.
Even intuitively, it's just going very fast.
Yeah, particles are this.
Geometric optics, what am I to understand that? Waves.
And if your energy say you've got a rest frame, and your energy is very large compared to the length scale of variation of that rest frame, then geodesic works. W. Just one. I'm saying it again. This is how I'm thinking of it, and just tell me if you think it's right, at least roughly right. I'm thinking of it as a classical potential that goes from 0 to 0.
Yeah.
So classically, there's no difference between the two zeros. But quantum mechanically, because this is peaked,
Yeah.
so there's a 0 point energy. Whereas this is infinite, so there's no 0 point energy.
Yeah.
There's a quantum preference to go from here to here.
Yeah, yeah.
And that
Yeah, that is the correct picture. Yeah. Okay, so one of the main argument that goes into discussion of instability of ADS was the slow quasi-normal modes of ADS black holes. And as I argued just now, these slow quasi-normal modes are understood to be related to stable trapping of geodesics in the asymptotic region of global ADS. And now we have a worse situation where geodesics are trapped in a compact region, and modes are decaying even more slowly. So for microstate geometries, the situation is much worse, and the decay is even slower. So let us go back. So in ADS, it suggests an instability because you put in a perturbation, and perturbation doesn't know how to decay, and it keeps on bouncing, and after sufficient amount of bouncing, the amplitude of this perturbation, when it comes back to r equal to 0, it grows and forms a small black hole. So this is how that argument for ADS instability goes. So the same argument one can apply here. One puts a small set of perturbation near this surface and let it evolve for a long time. Because these perturbations cannot decay, after after a lot of time, it will collapse to form a black hole. So this is the argument. Okay, so motivated. So after this Festucci and Liu analysis, these two mathematicians, Holzegel and Slunovici, they study in a lot of detail the decay of the scalar field in ADS. And what they showed is that the slowest possible decay in ADS is log t power -2. Yeah. The energy is.
So what exactly is happening for them to make it, for them to collapse?
This is you can think of like superposition of various modes in some sense. So this bouncing. Okay. So the way this works is that in ADS, so you let the perturbation fall. So perturbation is sufficiently weak, so it comes and then bounces back. But next time it bounces back, it sort of gets enhanced. Like locally it gets enhanced. So if you wait sufficiently long and wait sufficiently number of bounces, the perturbation eventually forms a black hole. This is what the numerical results. No, so yeah. This is this is why there is a question mark. They argued that you see in ADS where the situation is much better, even there this is happening. In microstate geometries, the situation seems to be much worse, and here also the same thing will happen.
Yeah, maybe I can make a quick logic. In ADS, at linear level, of course, nothing happens. Linear just repeats forever. The question is the non-linear. Okay, so now in ADS, if you look at the detailed mechanism in perturbation theory, what's very important is that the ADS spectrum has this feature that if you have energy, you've got modes at energy omega 1 and omega 2, there's also a mode at energy omega 1 plus omega, because of the quantization of these energy levels. So now, if you look at the right-hand side, let's say, of the sourcing of any given frequency, there are sources at resonance. Okay. Now, if you just had a single harmonic oscillator and you sourced at resonance, that's not a problem. It changes the effective frequency of that harmonic oscillator. But there are situations when you have multiple harmonic oscillators and you source all of them at resonance, when there's actually some sort of funny thing going on. You can't correct this just by changing frequencies. I think 3 or more harmonic oscillators is the minimum for this to happen. And this is the kind of situation you find yourself in. So very fast, you get some enhancement of things by nonlinear effects, some resonance effects, and that sort of starts blowing up. And it's believed that leads to formation of small black holes.
Yeah.
Is that accurate?
Yeah. This is.
existing black hole already and some.
No. So the Festuccia-Liu analysis was the first analysis where they did a careful calculation of these kinds of things, and they found there are slow quasi-normal modes. Then this subject sort of developed, and then people related it to the fact that because there is stable trapping of geodesics and perturbation can be stably trapped, there is something funny that can happen. And then this Bizon and Rostrovsky did a numerical simulation, and they found that that's the one. Yeah.
I see.
Yeah, but then it can be linked to the fact that there are these very slow quasi-normal modes for black hole, and this has some relation to.
That link I didn't see. The resonance mechanism seems to be
Independent of the.
different kind of.
But maybe it's related to the fact that suppose you form a very small black hole. Okay. Then basically what I said will be unaffected by that black hole, and that's essentially this very slow decay of this thing. Right? If it's very small, at least or even if it's finite, but as far as large L modes go, the black hole is invisible to these modes.
Yes.
That's why it's decaying so slowly. So other perturbations there get sort of smaller and then efficiently fall into the black hole. So maybe even black holes eat up stuff fast. I don't know if any of this is right. He's looking very skeptical.
But it may not be the same mechanism for fuzzballs.
That is correct.
Yeah. Okay. Yeah, that's why this question mark. So this is what these people suggest. So okay. So this is the next slide.
Also, you said that this situation is much worse.
Yeah, much worse. Yeah.
Tell me why.
So yeah. So first, the modes are longer lived, and they are not stably trapped in a non-compact region. They are trapped in a compact region. So if this collapse scenario has to happen, it will happen faster.
What was the case where it was stably trapped in a non-compact region?
ADS.
Oh, non-compact you mean up to infinity?
Up to infinity. Yeah. Okay. So motivated by Festuccia and Liu and so on, these two mathematicians calculated the rate at which the perturbation decays in ADS, generic perturbation decays in ADS, and they found that it goes like log p power minus 2. What is important is that slower decaying modes are with the larger L. This is what they found. And what I want to emphasize is that this behavior is very different from the black holes that I discussed in the first part of the talk. Eretikis showed that decay of scalar field outside the black hole is power law, with large L modes decaying faster. So here we see that there are clear qualitative differences between decay properties of scalars on fuzzballs and on black holes.
And this statement is independent of whether some big small black hole forms. This is just a linearized statement, right?
So yeah, this is every study so far is linearized, but this is a sort of a very calculational qualitative difference that we have found in studying scalars on fuzzball versus black holes.
Already at linearized order you see a difference.
Yeah.
So whether or not there are some differences in nonlinear order, already there's a puzzle.
Already there is a serious puzzle. Okay, so so with this I will say a few things about our paper and some debates that had taken place in this. So as in black holes, a new paper comes, there is a debate. So so ERS argued that stable trapping is a local effect. So perhaps it leads to a formation of tiny black hole, and the tiny black hole is very similar to what happens in the case of ADS instability. Okay, within weeks, these authors, Marolf, Michel, and Pum, they argued that yes, indeed, it is a local effect. So what this local effect seems to suggest is that alpha prime corrections are important. And what they argued is that fuzzballs remain fuzzballs, but they are corrected by alpha prime. That is to say that they have alpha prime related features. And also they argued is that, what they argued is that this instability can be anticipated from a discussion of entropy enhancement, in the sense that if you start with a very non-generic fuzzball, it wants to evolve to a situation where there are more density of states. So yeah, this is a problem. This is very heuristic. Then ERS went back and tried to understand whether alpha prime corrections are known for the relevant Raymond sector of type 2b supergravity, and they find that those corrections are not known properly. So such a calculation at present cannot be done.
Wait,
Yeah.
can't you find one example of a fuzzball solution where alpha prime effects are not important? Some artificial examples. Like in the two chart situation you put.
Yeah. So earlier people have argued that alpha prime corrections are not important, but this is a slightly different idea. Here one is adding this scalar field perturbation and this geodesics are moving and so on. So there is already some local effect happening, and the question is whether this local effect can be regulated by alpha prime corrections. So yeah.
But even though you could be working in a regime where everything is very large and length scale, straight scale.
Yeah, but still there is this very peculiar effect now. So there is a particle which is rotating on this surface,
Yes.
and the back reaction of this particle is what you want to understand. And the question is whether one can regulate. So the ERS argue that this back reaction is so large that it will make a black hole. But Marolf wants to argue that okay, the effect is large, but it will not make a black hole, but some alpha prime features will come.
Can this cure the linearized problem? There was some, forgetting about whether black hole is formed or not, you had a clear contradiction at linearized order. How can the alpha prime effect affect that?
Yeah. Okay, so let me say two things here. Yeah. So the thing is that after Eperon, Reall, and Santos pointed out that there is a nonlinear instability, people sort of forgot about the difference in the decay behavior of the scalar field. People focused on the instability per se, and a lot of effort, lot of debate has gone into what is the resolution of this instability. And not so much discussion has gone into what is the resolution of that puzzle that the scalar fields are behaving so differently.
These two are related or not?
The issues are very much related. I mean, the issue arose one from the other. Yeah, because there was a stable trapping, there was slow decay, and that led to the. Okay, well, Bena and Warner, of course, they don't agree with this. And they say that there are more detailed fuzzballs where this instability is more of a feature rather than a bug, and they have written some convincing solutions to that end. Like they argue that on this surface there is an instability happening, so one can try to construct a fuzzball solution where there are features only on this surface and everything else is almost the same as the previous solutions, and they have constructed such solutions. But whether they have addressed those puzzles or not, that is.
What do Bena and Warner disagree with? ERS or?
They disagree with the whole concept of whole debate that there is a instability and one should worry about this instability. They seem to say that this instability is more like feature that you throwing in particles and particles are getting trapped into the fuzzballs.
Wait, are they saying that the instability will lead you to some other fuzzball?
Yeah, exactly. So Marolf argument can also be viewed in that way, that the instability can be viewed in some sense to evolution to another fuzzball, and this is also what they want to argue. Yeah.
Then the new one, so their mechanism is not through alpha.
Okay, so this is their mechanism is like you can think of motion in the space of fuzzball solutions.
And
You
it'll
can,
keep going.
it will never stop.
But,
Yeah.
but the endpoint or never stop, so there is no endpoint.
If you add any perturbation, it will evolve again, and that's. But if you take any particular fuzzball and repeat ERS arguments, then it has again those problems.
But you're saying that there is a surface of solutions, which is the surface of fuzzball solutions,
Yeah,
and you never move far from that surface. You just move along that.
move that surface.
And so
Yeah.
they don't think that's an instability.
That's
You're always in the space.
always
of
in the space of solution. Exactly.
like billiard balls from atoms.
Yeah. Okay. Well, at least these are the few papers that have made published comments. If you ask other people, people have different opinion. People get frustrated and they say even detailed classical properties of black holes need not emerge from the fuzzball proposal. And to say the very least, all this is very confusing. Okay, so most of the previous authors were concerned about this nonlinear instability per se, with Bidisha and Debudrina, we were concerned more about the slow decaying modes and the spectral problem. And in the rest of the talk, I will discuss what we have done, and details can be asked to these authors. Okay, so we focus on the computation of these quasi-normal modes in the decoupling limit, where ADS-CFT is expected to be valid. And by ADS-CFT, we mean the D1-D5 orbifold CFT. Okay, there are debates about whether D1-D5 orbifold CFT is the correct description of the gravity and so on. So I have nothing to say on that, but I just take this 3-charge or 2-charge fuzzball solution, take the state identified in the D1-D5 CFT, and ask the question, can I reproduce the quasi-normal mode spectrum? This is the question that I am interested in.
Sorry. In the decoupling limit now,
Yeah.
where can this decay to?
Yeah, so there is ADS throat and there is asymptotically flat region. In the strict decoupling limit, the ADS throat is completely decoupled from the asymptotically flat region. But in the near decoupling limit, there is a coupling between ADS and asymptotically flat region, and this is precisely what we calculate. So through this coupling, we ask how slowly the perturbation stuck in ADS decays to flat space, and that is what gives the quasi-normal modes. Okay. So in this case, the scalar excitations are well understood, and we ask whether we can reproduce the slow decaying quasi-normal modes by such an analysis. Okay, so I will just give a very brief overview of this. So pure ADS is dual to NS vacuum in ADS3 CFT2. Then the solutions that I will study are these solutions. These are the simplest 3-charge fuzzball solutions. These are most symmetric. A scalar wave equation is known to separate. Geodesics are known to separate. Like many properties of these solutions are very well studied. And these solutions are simply dual to the NS vacuum, except that you apply spectral flows both on the left and on the right. So on the left, you apply only 1 unit of spectral flow. On the right, you apply 2n+1 unit of spectral flow. So you apply odd number of spectral flows on both sides, so you go to the Raymond sector. And since you apply odd plus some number, 1 plus some number, and this is what gives the third charge to the solution and energy to these solutions. Okay. So in this discussion, there is the twisted sector. So untwisted strings can get twisted like so. So we study minimally coupled scalar in 6 dimensions, and that scalar has an interpretation in 10 dimensions with graviton in the graviton with lex in the T4 direction. And bulk excitation corresponds to chiral primary states in the CFT. And these authors wrote down the normalized vertex operator that allows us to calculate the scalar emission spectrum from these fuzzballs. So actually setting up the problem was much more work than, like having clarity on the project was much more work than fishing through the literature and finding the right formulas and so on. So these people had already written down the vertex operator for such a scalar emission. So this is what we did. So using their results, we just compute this transition amplitude. So we have a excited state in the CFT where some of the strings got twisted, and this corresponds to a fuzzball with a scalar excitation, and the scalar field decays. So scalar field comes out, and emission happens, and the fuzzball becomes the simple Giusto Mathur section.
Emission to a closed string.
Emission, yeah, a closed string emission happens, and yeah, precisely. So
the excitation is what? Excitation is by a twist operation?
Yeah, exactly. So the scalar emission has been understood to be this process that a twist operator, initial state is some strings of the initial states are twisted, and if they become untwisted, then a scalar particle can come out, and one can calculate the spectrum.
Closed string mode that couples to that twist operator, and that is the one
that is the one that comes out. Yeah, it's very similar to what you guys did in the 90s. Okay, so remarkably, this process, just this simple exercise, gives the full quasi-normal mode spectrum, and the decoupling limit faithfully captures the ERS physics. And indeed, from this transition, one can indeed find low energy modes which in the larger limit behave like this. Like So this process has lot of parameters, L, M, energy, and all this. And if in this thing one takes the larger limit, indeed one finds that there are omega r which goes as order L to the 0.
Sorry, omega r
Was the real part of energy.
So that somehow has nothing to do with the decay.
Yeah. So that is the next slide.
Well,
Yeah.
wait, but before that, sorry. This was L of the
L of the perturbation. Yeah. L of the.
What is that?
Yeah. So the L, that's the L is the number of twisted strings that you have to consider. So if you consider 5 twisted string, then the emitted scalar will be in the L equal to 5 representation of
But
SO.
as you're changing the L, you're also changing the original fuzzball.
Yeah. So yeah, exactly. So we are putting a scalar perturbation on the fuzzball. So the state. Okay, this is a CFT calculation we are doing right now.
Right.
We don't know the gravity dual of this state. Yeah. So we take this state and twist it appropriately, and we ask if this state gets untwisted, what is the spectrum that we will get?
Twisting itself is not the perturbation, right? You've got twisted and then put something moving on it.
That is also one can do. But
but twisting is your perturbation?
we are considering this to be fuzzball and scalar.
Oh, this is off. This twist breaks supersymmetry?
The twist can or cannot, may or may not break supersymmetry. There are twisted states which are supersymmetric, but there are also twisted states which are not supersymmetric.
Okay, if it didn't break supersymmetry, it would stay extreme.
Yeah. If it, yeah.
And presumably would not decay.
Yeah, indeed. Yeah. So there can be situations where omega r becomes 0.
Okay. So okay, those are the completely.
Those are the. Yeah.
And but the ones you'd be most interested in are some sort of twists that break supersymmetry.
Yeah, and gives them slightly extra energy, and this extra energy can go out.
So that's what you're doing here.
That's what we are doing here. Yeah.
And is it clear that twisting L of these strings can be thought of as a small perturbation of the gravity? Sounds like quite a big perturbation.
Yeah. So this is what I said earlier. Chiral primary excitations in ADS3, scalar excitations in ADS3, a class of scalar excitations in ADS3 can be mapped to chiral primary, can be thought of as chiral primary perturbation. Chiral primary spectrum on the D1-D5 CFT side is well known. So indeed, there is a mapping that one can make that scalar excitations on ADS3 are related to chiral primary states in the CFT. So this is all that we are using.
Yeah, so if the twist operator is taken to be the very long string kind of twist operator,
In the larger limit.
Have very little energy. So if you have L of them, then you can still remain at small energy, which might.
It's small energy, but it just seems like the space of solutions looks quite far away.
Okay, so I have some comments on that. Yeah, I have some comments on that.
You're not like comparing between various L things, expressions of the same.
So actually this limits the way these limits work, I must say, is not very clear to me. What I thought is that you take N1, N5 to be million and take L to be 1000, and still the calculation would make sense. And even if you take L equal to 1000, this seems to be.
Okay. You're thinking L is large but not large compared to N.
Certainly we cannot make it close to N1, N5. Yeah, that is true. But L large, so that geometrical optics approximation makes sense, and can try to. Okay, so imaginary part. So typically in ADS CFT, one computes the correlation function in the CFT and compares to the quantity in ADS. Our setup is slightly different. We are interested in microstate geometries discussed above have an inner ADS region, and these geometries are, this inner ADS region is glued to asymptotically flat region. So what we are interested in is decay from this ADS region to flat space region. So the quasi-normal modes are determined via the outgoing boundary condition in the asymptotically flat region. Therefore, we are interested in the emission of a scalar quanta leaving to infinity in the asymptotically flat region. And this requires coupling of CFT to the flat space mode. And this is just like ADS, standard ADS CFT, yeah. But fortunately, this physics was worked out in the context of D1-D5 system by these authors, and they gave a formula. So they gave a formula that the emission rate to infinity is given by some factors times this transition amplitude. So F is the initial, F is the final state, I is the initial state, and they also computed the vertex operator for this. So we just calculated this quantity, and we computed this transition amplitude for the above process and took the large L limit, and this large L limit precisely gives the ERS results in the decoupling limit. So, okay, so this is all I wanted to say. Now I have some vague comments. Which
2 minutes, just so that we understand from the calculation why it's so small.
Yeah.
You say that you take the final state, which is this twisted guy.
Yeah.
The operator, which is the twist.
Yeah.
Whose action is acting on this, going back to the output.
Yeah.
Why is that? I don't understand intuitively why this amplitude is so small.
Actually, it turns out that this amplitude is not small. This amplitude is yeah. So it's just these geometrical factors which are very small.
And can you intuitively tell us what that means?
So what that means is that anyway, it's difficult for a perturbation to come out because the perturbation has to cross the exponential barrier. So
no, in the field theory, just from a field theory point of view, what are these factors? These are like phase space factors?
These are phase space factors. Yeah, these are just like how the large L angular momentum mode in flat space region is coupling to ADS modes. It's that kind of thing.
So it's basically completely insensitive to the physics.
Well, this is what we found, that yeah. So it is it's the kinematics, and also this also reflects the fact why the effect is so generic. The effect is generic because it's simply the physics of perturbation decaying from ADS region to flat space. In this, on this ADS CFT, in the ADS CFT discussion, and on the gravity side, it's just this discussion that zero energy geodesics are getting trapped on this special surface. So
something like that happened also in the original where you had amplitude excitations.
yeah.
But the phase space factor corresponded to the gray body factor.
Yeah. Actually, so this is something we tried for a long time. Initially, we thought that if we take the larger limit of the gray body factor, we will recover the omega I dependence. We were able to get the prefactors correct, but we were not able to get the full expression correct. But when we did with this formula, we got everything.
Is it the statement that a Green's function at large n has a barrier which determines this? Suppose I take just a Green's function at large n, just del squared n, look at it at large n. This will have a certain barrier, and tunneling through that presumably gives all of this, right?
Yeah, I think that is very true. Yeah, all of this will come out of that.
So any large L mode coupling to anything at reasonable frequencies will always have this in any theory, basically.
In the near decouple, in the
to working to first order.
Yeah.
Okay.
Yeah.
So if you had some electromagnetism, some source for radiation at large.
Okay. Yeah. This will also. I do believe that it applies not just to scalar perturbation, but to all perturbations of that type. Okay. So. Well, this is all the physics that I wanted to say, and all the calculations. Now we have a picture and some center. Yeah.
You know, your e to the power minus L log L is basically a 1 over L factorial.
Exactly. So this is actually, in retrospect, this is what we, So in retrospect, this was really just that, 1 over L factorial square gives e power minus L log L. But all the important thing is that all the other things give rise to subleading correction. I did not show the full formula. There are subleading corrections order L to the order L, order log L, and order 0. Those terms also come out.
The
Correct.
only comment was that in large D,
Yeah.
you get decoupling by the same 1 over D factor.
Ah.
And it's the same reason. The Green's function
The Green's function is of that type.
just
Yeah.
has this 1 over D factor.
Yeah. Yeah, I mean, actually the interesting part was that other factors don't give rise to any other non-trivial L dependence. It's everything, the main L dependence comes from this 1 over L factorial square. Yeah, and this is what is not there in the gray body factor. In gray body factor, there is a double factorial term, but not the single factorial term. There is some small differences.
And the 1 over,
Yeah.
sorry, L factorial square came because you took an amplitude,
Amplitude.
1 over L factorial and then squared.
Then squared
It's
it.
exactly the same.
Yeah.
So was it e to the power minus 2 in log n?
Yeah, it was my e power minus 2 log. Yeah. Okay, so the fact that we are able to reproduce almost all details of the ERS modes gives us some credibility to propose a gravity dual or say some things about what we think what is happening. So we believe, as Shiraz was also mentioning, so we believe that as soon as we put a scalar excitation, we change from one fuzzball to another. And since the new fuzzball is of slightly higher energy than the initial one, there is a small decay probability of going to the lower energy fuzzball. Okay, so although this statement is nonlinear, we don't know how to do anything nonlinear. What we have done on the gravity side is linear fields on microstate geometries, and on the CFT side we have done presumably a nonlinear calculation whose gravity dual is a nonlinear calculation, and there seems to be some discrepancy, debate, whatever. So it seems to suggest that linear fields on microstate geometries is not capturing the correct fuzzball physics. In particular, we see no evidence of this tiny black hole formation discussion of Eperon, Reall, Santos, and scalar absorption is responsible for the motion on the space of fuzzball solution, and we tend to align with the suggestions made by these authors, Marolf, Michel, and Pum, and Bena and Warner. Okay, so this is all I wanted to say. I will just end with a small summary. So ERS have pointed out that the decay behavior of scalar field on SUSY black hole microstate is very different from supersymmetric black holes. And if we just go by their arguments, so far I am not convinced that there is a way around these arguments. I mean, the arguments are so robust that this statement applies to all black hole microstate solutions that have been constructed so far. The decay on fuzzballs is too slow, and this suggests a nonlinear instability. There are proposals about endpoints of instability. ERS suggested that it leads to a tiny black hole formation, and then there is a debate. A main ingredient in the argument of ERS was this slow decaying quasi-normal modes, and we have shown that all such details can be faithfully reproduced by a D1-D5 CFT analysis. Based on this, we argue that the nonlinear instability is simply an evolution to another fuzzball. Though we do not have any nonlinear calculation to support our claims, the whatever calculations we have done, it seems to point in that direction. And it appears that linear fields on microstate geometries is not capturing the correct fuzzball physics, and this is related to this fuzzball complementarity discussion that took place 5 years ago. Okay, so thank you once again for the invitation. For more details, see our 2 papers. So on Ereticus we have done a paper, and I gave a talk on this last year. On ERS we have done a paper, which is this. And my collaborators on Ereticus are Srijit, Bidisha, David Chow, and Partho Paul, and on ERS is Bidisha and Deb. Okay, so with this I will stop. Questions? Yes. Yeah, ICTS I have given a same talk.
Maybe we should ask them. Yeah.
Any questions?
Sir,
Gopal?
Gopal questions.
They can't hear us.
Maybe they can't speak. Okay, while they're discussing, let me
Yeah.
let me ask you. Somebody's coming.
Can you hear us?
Yes, yes.
Yeah. So will you just tell me once more, like how your calculation was mapped? To the gravity side computations?
Yeah. So we proposed a picture that as soon as you put a scalar perturbation on a fuzzball, the CFT state changes to this one. So this is something we proposed, well motivated based on previous calculations. So we proposed that the scalar, as soon as you put scalar field on the fuzzball, the state changes to this one. And then we ask what is the spectrum of emission from this excited state to the unexcited state. So we calculated this spectrum and the decay rate and so on. And what we found is that the spectrum as well as, the real part of the spectrum as well as the imaginary part of the spectrum matches with the quasi-normal modes that Eperon, Reall and Santos calculated.
Okay, thank you.
Yeah.
Okay, I'm going to come back to this the linear, the log t square versus.
Yeah. Okay, log t square discussion. Yes.
Now you had an e to the power whatever. What was it?
Yeah. Okay. Yeah. So let me first. Actually, I must say that in the case of fuzzball, the exact dependence is not known. But okay, let me write the formulas. So ADS, the quasi-normal modes were minus e power minus some factor times L, and fuzzballs omega I is e power minus 2L log L minus. Okay, yeah. And then decay. So this is in ADS. And fuzzballs, there are some papers, but I must say I don't understand these papers, but it's slower than, expected to be slower than the above. I think this much I can say for sure.
Okay. So what is the suggested resolution for that? I'm assuming that your picture is correct, that somehow fuzzballs make up the black hole.
The mechanism, okay, these are words. I cannot do any calculation. The mechanism that is suggested for the decay is that all the perturbation is decaying to infinity. When we discuss this decay and in the fuzzball case, we never discuss any absorption at r equal to 0. Okay, all the boundary conditions were such that everything is decaying to infinity.
Right.
But now we have a different physics, different picture, that as you put in this perturbation, the fuzzball changes. So there is some fuzziness or some absorption also from the interior part of the geometry, and this perhaps can change the answer.
So if I sort of try to, so what you're saying is that you've got a space of solutions, and on that space of solutions there's no decay. But it's sort of like if you keep track of the atoms in a gas, their positions are not decaying.
Yeah.
But if you keep track of fuzzy stuff, like energy density or something like that, you'd see decay.
Yeah.
So some coarse graining will show you faster decay. Is that a fair summary?
I would not know how to set up such a calculation, but if one can take into account this absorption.
The absorption must be some coarse graining, right? Because otherwise, in the fuzzballs you've got a detailed space of solution.
Yeah.
It's basically we have the black hole absorption section of the working etc. by summing over all possible fuzzball states.
Yeah.
And that's how indeed it is. So one should think of one should expect black hole results to appear by coarse graining over fuzzballs.
Yeah.
Maybe the set of fuzzballs has some sort of natural cutoff where things are getting smaller and smaller and smaller and smaller.
Yeah.
And after that, any fuzzball that goes smaller than that, we call a black hole. And maybe what's happening is that your motion in the space of fuzzballs is going towards the small thing,
that.
and that's the decay. Could that be?
So Subrat and his student have some issue here to see whether very small fuzzballs and black holes
actually they are not here. They are better people to comment on that. I must say I never fully understood their arguments and claims. One of the things they wanted to say was that a basis of such states will be such that linear superposition will never give you a state which is close to black hole. This is one of the statements they wanted to make. But I must say I am not the right person to.
You know, I have
Yeah.
some questions which.
So just one comment. So because of this discussion, this is perhaps the reason why Bena and Warner are not worried about the conflict between decay property of the scalar field on fuzzballs versus the black
Yeah, it's
hole.
understandable.
Yeah.
It's obvious that from their point of view that there's no decay corresponding to going in the horizon because there's no horizon. So it has to be some other effect.
Some other effect.
Yeah,
And yeah. Yes.
I mean, I'm not saying it sounds right, but if you buy the fuzzball thing, it's not an additional thing you have to buy. It's part of that.
It's part of that. But it's interesting that although there are hundreds of papers and so on, but the Eperon Reall Santos paper did not mention any of this in their discussion, and they pointed out just take a fuzzball and do a classical GR analysis on it, then there is a puzzle.
Yeah, that's interesting.
So your system actually does not describe an extremal black hole, right? I mean, it has some energy, admittedly small, maybe L over L.
Yeah.
But it's still near extremal. The physics of the gravity thing is quite different.
Okay.
And it was really extremal.
Yeah. So actually, it's related.
Of a different kind.
Yeah. It's related to this linear versus non-linear discussion. All of Eretik's analysis is linear fields on extreme black holes, and this is the only thing that has been done in the near 5 years. I would say this is the only thing that can be done. So what we have studied on the extremals on the black hole side is decay of a linear field on a black hole background. Now, how do we? So the question naturally will be that can we compare this to the linear fields in fuzzball background? This is what Eperon, Reall, and Santos did. But our paper is about D1-D5 CFT and so on. So we have a picture where the state becomes excited. Now the gravity dual of that excited state is not known, and it's natural to expect it will be a nonlinear solution where some scalar field has back reacted, and I mean the geometry has been deformed. So that nonlinear discussion we are unable to make
So
precise in any way.
This is an excited black hole. You're saying that it is a scalar field riding
On a
external
fuzzball.
black hole, perhaps in that pocket potential.
I mean, in this picture, I am really thinking of a new fuzzball which I don't know how to write, but it's a fuzzball with scalar field and metric and Raymond field. This is what I'm thinking.
And it's near to one of the, it's near to some original fuzzball because it's near extreme.
Near extremal, it has very little energy also. Yeah.
We used to think of these excited configurations
Yeah.
as black hole solutions.
Uh-huh.
Excited black hole. I mean, near extremal, not extremal black hole. Near extremal black hole solutions. And they are going into the extremal black hole.
So this you would say is a picture, but summed over, like
So-
summed over, or
Yeah, so you're thinking of the left hand side
yeah.
differently from I would think of it.
Okay. I'm thinking of these as two different states in the CFT,
Different states, yeah.
and I'm not summing or averaging over either one of them.
Indeed, no,
Yeah.
that
Yeah.
point I get.
Yeah.
That point I get. We had some.
Yeah.
So we got, I see. How do you make this point that this is actually a scalar field excitation riding on a fuzzball black hole and not an excited fuzzball solution corresponding to a non-extremal?
I mean, the excitation will make
Maybe
it
it doesn't make a
non-extreme.
difference for you?
It doesn't make a difference, I think, because anyway, the gravity solution corresponding to this configuration is not known to me. But it's not known to me. Yeah.
Is there, and this is also
Yeah.
what I was going to ask, is there a map between these diagrams? Suppose we stick for a moment just to the extremal.
Yeah, these ones, yes.
Okay. That's of course very simple and probably the primary solution is.
Yeah, yeah, yeah,
But suppose I write down all 3 charge extremal solutions.
yeah.
Is there a map from that, from these CFT diagrams to solutions?
Yeah, yeah. So indeed, so this was a puzzle for many, many years, but this developments of superstrata, Bina-Warner, Shigemori, and so on, for a given perturbation on ADS 3 times S3, one can, I mean, so on ADS 3 times S3 perturbation, one can write in terms of the D1-D5 n equal to 4 superconformal algebra modes, and for each one of them there is a map one can find how the modes of the CFT are excited and what is the corresponding gravity solution. So indeed one can make a very detailed dictionary between such diagrams and solutions of the.
So you say that you don't know what that corresponds to, the left hand side corresponds to, because that was non-extreme. Is this right?
It's non-extreme, and the dictionary that those authors have.
It does not include twists.
No, it does include twist, but what they have is that the formulas are like superposition formulas in some sense. Like what this, so they go the other way around. They first construct a solution and then they try to propose a CFT dual. The CFT dual that they propose is written as a sum over many such twisted states.
Any more questions?